Hi everyone. This work is about reconstruction from compressed acquisition, that is from incomplete measurements. My name is Nicolas Ducros and I am with the University of Lyon in France. This work is motivated by fluorescence-guided neurosurgery. Previous studies have indicated that protoporphyrin 9 or PP9, which can be induced by ingestion of a drug, accumulates in higher concentration in tumor tissues. Therefore, the fluorescence emitted by PP9, here in pink, has been used to guide surgery, which was shown to improve the resection of high-grade gliomas through better detection of the tumor margin. Recent studies have shown that exploiting the full spectrum of PP9 can also improve the resection of low-grade gliomas, and this is why we are interested in measuring the full spectrum of PP9 in real time during surgery. So we need a hyperspectral imaging device. On the one hand, we have array detectors that can image in up to tens of spectral channels, but they are expensive. On the other hand, we have spectrometer that can image in several thousands of channels for a modest cost, but they can image only in one point. For fluorescence guided surgery, what we need is the spectral resolution of a spectrometer and the spatial resolution of an array detector, and obviously we would like to get this at low cost. This is why we will implement a compressive imaging modality. Compared to a conventional imaging setup that directly images the scene, here a nude mice, a compressive imaging setup images this scene in a transform domain, usually a spatial frequency domain such as Fourier or Hadamard domain, and this raw data has to be reconstructed to recover the image of the scene. So this is more complex, but you can get an improved spatial resolution or get a richer information content such as an extra wavelength here. Here's our compressive imaging setup. It's a single pixel camera because it has only a point detector. Light goes in here. It is coupled through this optics to, it is focused here onto a special light modulator. We have here a digital micromirror device which consists of millions of micromirrors that can reflect light in two different directions. When light is reflected in this direction, then it is coupled to our spectrometer through an optical fiber. How do we perform an acquisition? Then we upload a pattern onto the DMD. So here white means that light will be reflected towards the spectrometer, and black that light will not be reflected toward the spectrometer. And for this particular pattern here, we measure this particular value here. Then we upload a new pattern, get a new value, new pattern, new value, and so on and so forth. And this is how we collect the raw data. Now let me introduce some notation. Let M be the measurement vector. So we assume here we have capital M measurements. Let P1 be the pattern matrix, which contain all the patterns that we use for acquisition. Here each pattern has n pixel. We have a linear forward model, so M equals P1F. And as measurements are performed sequentially, we want to only have a small number of measurements, capital M, to limit the acquisition time. This is why we are in this configuration where we have here a flat P1 matrix, and the challenge is to reconstruct the image with a good spatial resolution with only a few measurements. Reconstruction now. Before performing the reconstruction, we have to design the experiments. We have to choose the patterns. This is a very interesting question, but I will not address it here. I will just say that we choose our patterns within an orthogonal basis. P, so P is the full basis. P1 is the matrix containing the acquired patterns, and P2 the matrix containing the missing patterns. In the following, I will consider Hadamard patterns. For reconstruction, which is the recovery of f from the measurement m, the classical way of doing this is through constraint optimization. So we minimize a regularizing functional r such that the recovered image is consistent with the measured value m. We can choose least squares as the regularized functional. This is fast because we have an analytical solution, but this leads to low resolution images. So we have parsimony promoting alternative that leads to higher resolution, but that are time consuming because we have to implement iterative algorithms. More recently, it has been proposed to use some nonlinear models, usually convolutional neural networks, to reconstruct the image directly. So directly in the sense that we have to learn this mapping edge theta here, where theta represents the parameters of the network, but then we just input the measurement to this model and it outputs the images in a real-time manner. So now I would like to talk to you about the main idea of this talk, which is to recast the reconstruction problem as a completion problem. So to do so, let's have a look first at the closed form solution we have when we consider least squares. For least squares, we have this solution where f star is given by p1 transpose times f, which is equivalent to building a vector y star here, where we have m as the measured value and zeros for the missing coefficients, and we multiply this by p transpose on the left hand side and we recover the least square solution. So the idea here is to replace those zero values by some relevant values to improve the quality of the reconstruction. How to do so? Well, let's have a look at a very large number of images by considering a database. So here I took the STL database, I computed the Hadamard transform of each of these images because we consider Hadamard patterns in this work, and our single pixel image camera actually measures the Hadamard patterns. And here I plot the Hadamard coefficient number 7 with respect to the Hadamard coefficient number 2, and each dot in this plot is an image. This is image 1, this is image 2, 3, 4, and so on. If we have a look at the Hadamard coefficient number 2, it's Gaussian light with zero mean. Hadamard coefficient number 7 is also Gaussian light with zero mean, but if we measure 20 for this Hadamard coefficient number 2, then it is very likely that we will get 10 for the Hadamard coefficient number 7, and this is this kind of correlation between the measurement that we want to exploit to complete the measurement vector. Here's our completion approach. We complete the measurement with some inferred value, and we infer those value by computing the this condition expectation. So this is the expectation of the missing coefficient for a given value of the measured coefficient, and under Gaussian assumptions for the vector y we have this very nice analytical formula, very simple. So basically you center the measurements because mu1 here is the mean of the acquired coefficient. You divide it by the covariance of the measurement, you multiply by the covariance between the measured and missing coefficient, and you add the mean value of the missing coefficients. And if you cannot make this Gaussian assumption, then this is still the best linear solution you can get. Now I'm going to move to learning-based reconstruction. So reconstruction can be done through convolutional neural network. This very simple architecture was proposed for single pixel imaging by Higam and co-authors in 2008, but similar architectures have been proposed for other reconstruction problems such as CT or MRI. So we have two parts. This is fully connected layers that maps the measurements in RM to a row solution in Rn, and then we have convolutional layers. If we look at the number of parameters in the network, we have 1 million parameters for the fully connected layer, and we have only 4 1000 parameters for the convolutional layer. So this is really important to understand what is going on in these fully connected layers, because it does most of the job. Our idea here is to plug here our Gaussian completion reconstruction. This is possible because a fully connected layer actually implements a matrix vector product, and our Gaussian completion reconstruction is a matrix vector product. Then we want to keep the convolutional neural network layers to compensate for the non-Gaussianities of the data. We actually compared three alternatives for the convolutional, for the fully connected layers: the free layer, where we learn the FCL; the pseudo-inverse, where the raw reconstructed image F tilde is given by the pseudo-inverse, which is common in different reconstruction problem; and the Bayesian completion scheme. We have three network variants: free net with 1 million parameters, the pseudo-inverse net, and the completion net with 4K parameters. Here are our results. We've trained this network with using the STL10 database. It has 1 million images. We tested it using 8,000 images. Here we have the results in terms of PSNRs. The worst PSNR is given by the pseudo-inverse solution, and this is really improved by considering the linear completion scheme. We have 1.5 dB of improvement, which is quite huge. We only have a slight improvement by considering the pseudo-inverse network, 0.1 dB, which means that the completion approach already does a really good job at reconstructing the images. This we have an improvement of 0.5 dB by considering the completion network, which is very similar to what is obtained with the free network, but here I recall that this network has much fewer parameters. We've also tested our network that was trained using STL on fluorescence microscopy images not taken from STL. So here we have the grand tooth image, the pseudo-inverse solution, total variation solution, and the completion network. So you can have a look at what is visually the difference between the different solutions. And in terms of PSNR, we have a huge improvement that is provided by the total variation solution. We have an improvement of about 3 dB compared to the pseudo-inverse solution, and the completion network further improved this by about 1 dB. And another interest of the completion network is that it can be computed in real time, which is not the case if you consider the total variation solution. Conclusion. So in conclusion, we propose to recast the reconstruction problem as a completion problem. We proposed a very simple linear reconstruction, which is based on Bayesian completion. We've plugged this linear reconstructor in a nonlinear convolutional neural network, and this seems to work quite well, at least on the image we assessed. We are working on providing some code to the community, so we already have a Bayesian completion MATLAB code available on GitHub, and we are working on a release of our convolutional neural network. This should be released soon. In future work, we want to process experimental data, so we will have to be very careful to what is going on when you introduce some noise in the data. And we are also working on taking into account and exploiting the redundancy that we have in video sequences. If you want to know more about this, don't miss the talk by Antonio tomorrow morning. Thank you very much for watching this video. Bye bye.